So first of all, we have to load in the voice recording we made. So we have input and the FS, which is our sampling rate, and we use the audio read function to load this in. The audio read, and then we use our name of the recording, which is just recording.wav. Now we have an FS and an IP value, and now I can just play this back to see if it works. Using our sampling rate, which is 44,100. This is OgnjenLovicC. So yeah, we can see that works. And now I have two columns here. I'm just going to change this to a single column, so it makes it easier for my other actions. There we go. Now we have a single column here, which will help us later on. So now that's the first part done. The recording speaking and played it back, and then we stored sampling frequency in FS. I want to plot the speech signal against the time in seconds and label the axes. So you make a time vector, so we do to go 0 through the length of our IP minus 1. The reason we do minus 1 is just because MATLAB starts at 0, so then you have the same amount of samples. We divide this by our sampling frequency. This will give us our time vector, and now we can just plot T and IP. So as you can see here, this is our plot, and now I'm going to just label the axis. So Y label. Y label is our amplitude. And our X label is our time in seconds. If I bring the plot back up, we can see it's labeled there, and the signal is around 2.6 seconds long. So there's that bit done, and now we want to copy this code to get our tone frequency and noise cutoff. So I'm just going to copy and paste it in, and delete all this. Now for this code, let's see, I have a tone frequency of 2118 and a noise cutoff of 17928. That's grand. So that's that bit done. Then you synthesize a high frequency noise and add a tone and add these to the speech signal. The way we do this is we just create a noise, so this is just a random that's the same size as our IPs. These are just random noise that we're going to add, and then we're going to filter it to get high frequency noise. So that's that done. You see it's the same size as our IP. So then we want to filter this equal to filter. Sorry, we're going to filter this using the butter function. Let's get 6th order, and this will be our noise cutoff. And then this is divided by our frequency over 2. And this will go to our B&A coefficients. So as you can see there, we have B&A coefficients. Now we can filter this signal. So NS is equal to filter B, A, and NS. This will just give us all the high frequency noise from this signal that we can add to our original one to make it more noisy. We also want to add a tone. So let's make a random tone here. Our tone is equal to 0.1 cos 2 pi times the tone frequency. And then times T. Times T. Times T. Now so we have a tone here as well, and we'll just add all these three together. Signal is equal to input plus tone plus NS. Do I get an error here? Yeah, we do. So we want to just... The reason we get an error here is because this tone is column, so we're trying to make it a row, so tone is equal to just tone. So we're just changing that, so we just change that to a row there, and now we should be able to add them all together. Signal is equal to tone plus signal, original signal, plus NS. Oh, sorry, our signal is equal to tone plus our input plus our NS. And now see that we have a signal value. If I just plot sig, you can see it's a really noisy signal now. So these are added, and I'm going to design a second order filter using MATLAB's butter function with the cutoff frequency set equal half the noise cutoff frequency. So the way we do this is just use the butter function again to get B&A coefficients. So B&A is equal to butter. We just put our parameters, so first the second order, and then we want half the noise cutoff. Just go noise cutoff, and this is divided by 2, and then once again it's divided by fs over 2 to just normalize it. Now we should get our B&A coefficients there, which we do. So that's done, and now we want to draw the signal flow diagram and the difference equation, which we'll do now in Paint. So now if we see our these are our B&A coefficients. So now we'll just draw this out in Paint. So here we have 2 delays. We're going to have 2 delays that go up and add. We're going to have 3 multipliers. These are all going to get added. Plus, we're multiplying. So these all get added together. This will be our X end, so our input. And this is going to be our Y event, so just our output. And this is just going to have 2 delays as well for the outputs. This is also multiplied. And then we just add all these together, and this will give us our figure. Let me just put the D for the delay here. Okay. So our A coefficients are 1, minus 0.3452, and 0.1927. So if I just put these in now on our Y side, we're going to have, it was 0.3452, and this is going to be a positive because it's on the Y side, so it's going to be positive. Just move it. Where is it? Right here. There you go. It's going to be 0.3452. Let's make the font a bit bigger. 0.3452. And we multiply there, and it's going to be minus 0.1927. Minus 0.1927. And these B ones are just going to be all the same. So 0.2119. 0.2119. 0.4237. 0.4237. And 0.2119 again. 0.2119 again. So there's our signal flow diagram that's shown here. Now we can draw the difference equation from the signal flow diagram. So here we have bigger fonts. Now we can say Y of n is equal to X of n. It's 0.2119 X of n. X of n plus 0.4237 times X of n minus 1 plus 0.2119 times x of n minus 2. And now if we do our y's, we have plus 0.3452 times y of n minus 1, and then minus 0.1927 times y of n minus 2. Minus 2, sorry. So there's our signal flow diagram and our difference equation that we can now use to get the first three outputs by hand. There's that part done. Now we want the first three outputs of the system. So I'm just going to go into MATLAB to do this. See what the equation is. So then, yeah, y of 1 will be, y of 1 is just going to be the first. Alright, we need to get the first three inputs from the signal. Sorry. So signal 1 to 3 will be our x of n's. So these are our first three inputs of the system: 0.0933, 0.1588, and 0.6251. So this will be put into the system. So for the first one, it's just going to be very simple. It's just going to be the equation here. Sorry, yeah. So it's going to be 0.0933 multiplied by 0.2199. And this will be our first input. 0.2119 times 0.093. This will just be our y of 1. So y of 1 is 0.0198. Now y of 2 is going to be 0.2119. 0.2119 times the second input, which is 0.423, no, which is 0.1588. Plus our second x, 0.4237, times our first input, 0.093, 0.0933, and then this will be added to 0.3452 times our first output, which is 0.0198. This will give us our y of 2 value, which is 0.08. And now if we do y of 3, which is 0.2119, times our third input is 0.6051, plus 0.4237, some brackets, 4237 times 0.1558, 588, and then plus our third one, 0.2119, times our first input, which is 0.0933. Yeah, so then 0.02119 times 0.093 plus some brackets, plus our two are delayed outputs, so plus 0.3452 times 0.08 minus 0.1927 times our first output, which is, I don't need this anymore. Go. 0.0198. 0.0198. Now this will give us 0.2433. If I want to confirm this, I can just go y equals filter using my BNA coefficients in my signal. I can just go y 1, 2, 3, and these should match. Let's go 0.0198, 0.08, and 0.2433. So now I've confirmed that these match my hand calculations. Right. So there you go. This is the first three outputs combined, and that's done. And this is also. I want to design a minimum order filter which will reduce high frequency noise by at least 60 decibels and a max of 3 dB ripple in the passband, and the passband 0 to fs over 4. So just 0.5 in the normalized frequency scale, because fs over 2 is 1. You do here is go n and omega, and use the buttered function, not the buttered function, the buttered function. We specify our normalized frequency, we go noise cutoff. This is divided by fs over 2. Normalize it, and we have 3 allowed in the passband and 60 dB here. So now we see this tells us our filter order and our frequency. Now we just use the butter function to filter this. We just sub in our n and omega, and there we go. BNA coefficients and filter designed. Now we want to design a second filter using MATLAB functions to reduce the tone by at least 40 dBs, and we want to ensure the system is stable. So what we do here is create new BNA coefficients because we still need the old ones. We use the butter function, and we're going to design a fourth order system so it stays stable, and this will be our. We're going to choose a frequency range of around 100. So we're going to go 2118, which is our tone frequency. We go minus 50 and 2118 plus 50. Just to give us our 100 frequency range that we'll be looking for. And again, this is divided by fs over 2. Fs over 2. This is going to be a stop band filter. Stop. Okay. There we go, now we have our BNA coefficients, and then we want to see if this filter is stable. We just do this by going to the z-plane function and looking at the graph. So this is stable if there are no poles outside the unit circle. I'm just going to check here. It looks stable from here, but let me just zoom in. Yeah, you can see there's nothing outside the unit circle, so therefore the system's stable and the filter's stable. We also want to ensure that it attenuates by at least 40 dBs. So you want to get our tone frequency. I'm going to divide it by our fs over 2 to see what radians we should be looking at here. About 0.0961. Let's go to the freak set of B1A1. And this third parameter is just giving me a smoother graph. We're picking more points. Then if I zoom in here, you can see around 0.9096, we have like around 90 dBs of attenuation, so that's perfect. That's what we're looking for. And the system is also stable. Now we want to apply both filters to the combined signal and plot the magnitude frequency content and output in hertz, what the axis is labeled. So we just do is y equals filter using our first BNA coefficients and signal. This will filter our first signal, and then y1 is just same again using our different coefficients and BNA coefficients and using our y output. Now we just want to plot, make a frequency axis and plot this. Frequency axis 0 to the length of IP minus 1. This is divided by the length of IP times our sampling frequency. And this will create our hertz, our frequency axis in hertz. Now we just plot frequency axis and the absolute value of our FFT of our signal of y1, or signal, sorry, and then we'll plot y1. Oh, sorry. And then we're going to plot our new one of y1. Now I should see here. Oh, sorry, it didn't hold on. Maybe hold on. Signal, and then we're going to hold on. And you can see already that the high frequency noise is filtered out. Now if I compare, we can see this high frequency component's gone. And we're going to have a much smoother output here. You can see that's gone. Oh, I'm going to label the axis as well, sorry. I'm going to go Y label, magnitude, and X label, frequency in hertz. Okay, now you see that's done. Now, for the last part of the video, I want to identify a low frequency component that's going to produce a phase shift in the first filter of at least pi/4, which is 45 degrees. I want to pass that through the filter and verify that this is altered by the correct amount. Just close this. Now we're just going to go and get the frequency out of BN8. Let's see what radians component we can identify here in the phase. So this is already in degrees here. Gonna zoom in. 45 degree. So I'm gonna move across. Look for a shift of at least 45 degrees. So probably so around here, I'd say. It's 44, so we need a bit more. See here. So this will be correct. This is just above 45. So I think we use this one. Let's get it. So 0.134. So 0.135 is what we'll do. Now if we close that, we have 0.135 times the sampling frequency over 2 times fs over 2 will give us in hertz what we need to change. Let's do this right. So yeah, that's about 2,980. So that's all we need to add to this tone. So now we go tones equal to tone. This will be our original tone actually, sorry. Look for a tone. So tone is equal to cosine 2 pi times 2,980. 2,980 times t. This is our new tone frequency. Now we're just going to pass this to our filter. Y equals filter. Using our BNA coefficients and our tone. That'll give us our Y. Now I can just close all and plot my tone against my original to see the difference. Plot tone, hold on. Then we're going to plot Y. And I should see at least a 45 degree phase shift within these. Now if I just zoom in. Scroll up here. Go up here a bit, and then maybe I want to get a bit more. There we go. So if I zoom in here, can we see at least, so that's an 8, so can we see at least 8 of these? 5, 6, 7, 8. Yeah, we can fit that in there, and that's just 1/8. So we confirm that's at least 45 degrees phase shifted. So that we can agree that that has been altered by the expected amount. And that completes our checklist. So we've done everything here, and that should be that. Thank you.